Hello everyone, welcome to discussion 7 for 61B. Today we're going to be talking about asymptotics and binary search trees. So first things first, let's get some announcements out of the way. First of all, midterm 1 regrades are going to close this Friday. Please submit regrades even if you're not sure whether you deserve the points. We grade a lot of tests in a really short amount of time, so we are bound to make mistakes. Don't let those points go unclaimed. Second of all, homework 2 is at this point already been due last Monday. Homework 3 might already be out at this point. If you feel like you are struggling in this class, like you can't keep up, please sign up for tutoring sections. You can find more information about that on Ed. It's only there to help you. So let's get to some content review. So before we get into the actual topic of this discussion, let's talk about abstract data types. This is another case of us kind of already showing you something and then giving you a name for it afterwards. So what is an abstract data type? An abstract data type is a data structure where we know what they do but not how they do it, hence the abstract part. So an example of an abstract data type is a list or a map or a set. And so in Java, these abstract data types are like interfaces or abstract classes, so you can't directly instantiate them. Instead, we make concrete implementations of these ADTs, such as array list and linked list, or hash map and tree map, and those are the things that we actually implement. So basically the list tells you, oh, you should be able to add things, you should be able to remove things, you should be able to get things, but it doesn't tell you what the underlying structure of the list is. That's what array list and linked list are for. So today's actual data structure is binary search trees. We're going to mostly be going over a conceptual overview. The lab this week will involve you actually implementing a BST, and that will be the general theme for the data structures portion of this class, where in discussion we'll kind of go over a conceptual idea of it and kind of like visual ideas of it, and then in lab you guys will implement it using code. So what is a BST? Well, the first thing is that BSTs have some important properties. So every node in a BST is a root of a smaller BST. So we have this BST here. This node is the root of our big BST, but if I look at this node and I just block out it and all of its children, we see that it's also a smaller BST. So every node is a root of some BST, and every node to the left of a root has a value lesser than that of the root. So if we go to this side of the BST, all three of these nodes over here have a value less than the root. Same with the other side. All of the nodes, all three of them, not just the one that's directly connected to the root, has a value greater than that of the root. So in general, BSTs, we kind of describe them as either bushy or spindly. And so bushy means that every node has like the max number of children for the most part. It's wide instead of being deep. And so bushy BSTs are good because the distance from the node that is the furthest away, to our root is log n. We also have spindly BSTs, which are BSTs where like we don't really put stuff on one side or some reason, and so it takes n time to get from some leaf to some root. And we will cover later in this class methods of trying to keep the bushiness of a tree, but for now, the only difference between a bushy tree and a spindly tree is the order in which you put elements in. So if I had like 10 elements, right? If I put 5 in first, and then I put in like 3, and then I put in 7, and then 1, obviously, and on like that, you'll see that it'll get bushier. But if I put everything in increasing order, you'll have 1 at the root, and then 2, and then 3, and then 4, and obviously that becomes very linked list-like, which is not as efficient as a BST. So how would you insert items into a BST? So items in a BST are always inserted as leaves, no matter what. So 2 here is technically between 1 and 3, but we still insert it as a leaf. And so what do? We compare first our item, which is 2, with the root node. So 2 is less than 5, so we'll take the left side path. And now we compare it against 3, and again 2 is less than 3, so we take the left path. And then we get to 1, and we're like, okay, 2 is greater than 1, so we'll take the right path. And now there's nothing here, so here's where we insert our item. Deletion's a little more complicated. So items in a BST are deleted by a method called hybrid deletion. And there are a couple different cases that you have to consider. So the first case is the easiest, in which the node has no children. So in this case, we would be deleting like 2 or 4. It's a leaf. Since there's no children, it's an easy process, right? We just get rid of it. Doesn't really matter. Nothing else needs to be changed to make this happen. The second case is when there is 1 child. And so when a node has 1 child, it just replaces the deleted node. So all that's happening here is we're deleting 1. So 2 is taking its place. Since we know that there's nothing over here, how do I show that? And 2 it doesn't matter how many children 2 has. We know that 2 is going to be less than 3. We know that there is nothing here to worry about, so we can just kind of pop 2 up into that spot and be done with it. The last one is the hardest case, in which you have to delete something with 2 children. And so this is like the big fancy algorithm case. And so when you are deleting something that has 2 children, so in this case 5, you'll want to pick either the leftmost node on the right subtree or the rightmost node on the left subtree. Now, why is this the case? So the idea is you want to reduce the amount of operations you have to do while still maintaining the BST structure, right? So the BST, remember what we said, it has 3 rules. The rules are everything to this side of our root has to be less than our root, and everything on this side has to be greater than our root. So we have really 2 options to consider, right? We need to find either the greatest item in this subtree, since we know that it'll be bigger than everything here and smaller than everything in the other subtree by virtue of being on the other side of our root already, or we can find the smallest item in this subtree. So what we do is we enter our subtree, we start here, and once we are in this tree, we literally just keep going to the right until we hit a node which has no right child. This node can possibly still have left children. So it's possible for 4 to have a child here, in which case we would pop 4 up here, and then we would kind of pretend like we just deleted 4 and pop this node up there. So basically, we replace it either with the smallest item on the right side or the biggest item on the left side. And it's up to you to pick. They do the same exact thing. And we're about to start our worksheet, but right before we get to that, let's just quickly go over some important points about asymptotics, just reiterating some concepts. The first thing is asymptotic analysis is only valid on very, very large inputs. So don't get confused if like your algorithm works one way when the input's 5 and 10 versus when it's 500 and 1,000. All of those numbers are way too small. When you think big numbers, I want you to think big numbers, because what we're measuring in reality isn't its runtime on a specific input. We're measuring its order of growth, right? We're kind of figuring out what speed does it grow at, and the way we approximate that is by picking a very, very large input. So don't get caught up on individual cases when it comes to asymptotic analysis. Solve it in terms of the input size. The next thing is, I've seen some common themes being said on things like ed and in person, like trees are always 2 to the n and nested for loops are always n squared. And while those can be kind of helpful in guiding you, they can easily lead you astray. Because nested for loops aren't always n squared, and trees aren't always 2 to the n, and it's always on a case-by-case basis. So if you're really stuck, I guess you can start from there and see how the problem you're looking at varies from the kind of mold that you've seen before, but you're best off always basically starting from scratch. And number 3, doing problems graphically can be really helpful if you're a visual learner. When I took this class, you should see my final. I had like trees for my asymptotic analysis problems all over, and it really genuinely helped me because I am a very visual person, and so doing the math, I was always unsure of my answer. But being able to be like, oh, okay, so this has n work and this has n work, and then I just have to take the sum of this, it made me a lot more confident in my answers. So I highly recommend you try it out. Maybe it works for you, maybe it doesn't, but you should give it a shot. This is just an example of a possible visual explanation. So the reason why 2 for loops when this I goes to n and j goes to I is still n squared is because when you basically have this triangle. It's actually n to 0 is what I just realized or something. But you have a triangle shape, and that is n squared time. So let's get on to our worksheet. The first problem is a pretty standard warm-up problem about binary search trees. We're going to talk about runtime. So for this first part, let's pretend you have an integer BST that contains n items. You don't know anything else about this BST. You can't make any other assumptions. So what is the asymptotic worst case of each of these functions? I'll give you a second to think about it, and then we'll reconvene. Okay, welcome back. Let's talk about it. So for add, let's see, what is the worst possible case for an add function, right? So let's say, what if our tree looks like this? Like I said, what if it's as spindly as possible? And let's say the node you want to add is somehow greater than everything else that's already in our tree. So what we want to do is add it here. How long will it take to add that? Well, you have to travel through every single item that's already in the list. So this will take theta n time. And the reason I'm using theta notation and not big O notation is because when I say the words worst case, I am restricting inputs to only the inputs that cause this worst case. And at that point, our tightest bound can be a theta bound. The best case is the same way. If I said upper bound, however, I would want you to give an upper bound over all inputs. And since the lower bound over all inputs and the upper bound over all inputs isn't the same value, because think about it. In this case, what if you wanted to add it here, right? No matter how many items n you have, if you wanted to add it on this side, then you're basically set. It's only going to be theta 1. So if I wanted you to upper bound it, you would have to use O of n. And then if I wanted you to lower bound it, you would have to use omega of n. And for part 2, this is basically the same thing as add for get min. Just imagine that your spindly tree is as spindly as possible and it's in the direction that you want to go. So get min will require you to hop all the way down, until you get to that point. So this is also theta n for the worst case. Now we're going to do the same exact problem, except this time you can assume that the BST from part A is certain to be bushy. Don't worry about how we can ensure that, but all you have to know is you know that the BST is as bushy as possible. I'll give you a couple of seconds to think about it. Okay, welcome back. Let's do this problem. So this time we can't have any spindly trees. We're basically locked into a tree that kind of looks like this. And like I said before, when a tree is very bushy, the height is going to be log n. And so since the height is log n, that means the furthest distance from any node to any leaf, any root to any leaf, is log n. So if I wanted to add, no matter what, I would have to make some log n comparisons and add a node maybe right there. It doesn't really matter. So the worst case will be theta log n. And the same thing will apply for get min, where you can go this way, and this is our minimum value. Log n. Great. So now we're on to some fun stuff, an actual writing code problem. So the first step is implementing the find function for a BST map. So I don't have that written down on mine, but on yours you should be able to see that there's a node class that has a key and a value in addition to a left and right pointer. So basically we are sorting our BST based off of the key, but we use that key to find a specific value, which is a very, very common thing to do in the real world. So I've already given you kind of a hint that we do need a helper function. So I'll give you guys a minute to think about it, and then we will reconvene. Okay, welcome back. Let's talk about it. So the first thing, let's fill out the helper function first, right? So the goal of this helper function is to return the value at that node associated with that key. So let's see, and then null otherwise, right? So what's our base case? Well, the first thing is, if we end up in a position where our node n is null, so basically if we somehow end up in a situation where we go, and we're like, this doesn't match, and then we go here, and like, oh, this doesn't match either. And then we go here, and we're like, oh, there's nothing left, the tree's over. Then we know that the key just doesn't exist in our tree, right? So the first thing we can say is if n equals null, return null. Oh, I want to mention something about this. So I've seen when grading midterms and stuff like that a lot, that a lot of people want to use n dot equals null when they are testing this case, because we've told them a lot, oh, for objects you always use dot equals. This doesn't work, and the reason is because if n was actually null at a certain point, null doesn't actually have an equals function, right? So if you did null dot equals, that errors. So if you're checking for null, or if you're checking that an object is null, you should always use equals equals instead of dot equals. Just an important aside that I thought I'd mention. So we have that base case, and our second base case was, well, what if we actually find the node that is associated with that key? So then we'll go if key equals n dot key. Working with integers here, so we can use equals equals. Return n dot value. Oof, I really messed that up. Okay, give us a second. There, so that is our two base cases. Either we decide that the node that contains that key is not in our structure at all, or we find the key somewhere and we just return the value. So now I have to figure out what our two recursive structure, recursive whatevers are. So the first case, we'll do else if here. Else if our key is less than n dot key, so the node we're currently on, if our key is less than the key at that node, well, we know that that means if the key exists, it's going to be on the left subtree of our node. So all we do is we return our same helper function with the same key, except we pass in n dot left. And then the last case is automatically, if our key is greater than n dot key, we do the same thing except with the right. So we do return find helper, key, and dot right. And that's our helper function done. So all we have to do now is figure out what initial value are we going to pass into our helper function in find. So if you notice in your declaration of the class on your piece of paper, we have this node head that kind of acts like a similar to like a sentinel or a first pointer in a linked list. And so what this is sort of our initial guess. So return, find helper, key, and head. And it'll return the value if there is one, and return null otherwise. Fantastic. Okay, we got through our first coding problem. And now we're going to kind of switch gears mostly into asymptotics. So the first problem is this double loop situation. So I'll give you guys a couple minutes to think about it. Your goal is to find the worst case and best case runtime in theta notation in terms of m and n. So you're going to find in terms of two variables this time. Okay, welcome back. So let's look at our function. So the first thing we can see is that the inner for loop doesn't actually depend on the outer for loop at all. Looking at this chunk, there is no I anywhere, right? So we can kind of basically figure out this inner for loop independent of the outer one and then later deal with how those combine. So what is the worst case, right? Well, the worst case is that we increment j as slowly as possible, which implies that we always enter this portion of our code, so command always evaluates to be true. So in the worst case, it's just a normal for loop where j increments by 1 each time. So we have m, and in the best case, we go this one each time, and so command always evaluates to be false. And so instead we have log m. And I can look at the outer loop, which is always going from 0 to n no matter what. So all we have to do is multiply this by n and this by n. So our actual answer is theta n m and theta n log m for worst and best case. Now we're going to do one that's a little more tricky. This is actually only partially a asymptotic problem. It's also about just writing faster code. So first of all, let's talk about what this function does. So the goal is going to be to write a faster version of it. But first we should probably figure out, what it's trying to do. So we're passing in some array A and some integer x, and it looks like what we're doing is we are picking up one item out of A and then the second item out of A. And we're returning true if those two things summed together is equal to x. And we're going to do that for every possible combination of items in A, and if none of them equal x, we return false. So what this is doing is it's trying to find if there exists two indices I and j, they might even be the same indice, such that AI plus AJ equals X. So this is a naive solution, and I want you guys to try to figure out the faster, better solution to this problem. Might be a little more complicated though. Okay, welcome back. So let's figure out how to do this. So let's talk about this conceptually first. This is a hard problem. It requires a little bit of out-of-the-box thinking. So let's say you have an array. And of course, like I said, this array is sorted already for you. Let's start off with pointers on this end and that end. So let's say we compare these values. We're like, okay, this first pointer we'll call left, and this right pointer we'll call right. We say, is left plus right equal to x? And if the answer is yes, then great, we're done, we return true. If the answer is no, we can ask 2 more questions, right? Is it too small or is it too big? So if our value is too small, how can we improve our guess? Well, if our value is too small, that implies, since this is already as big as it can possibly get, that implies that we should move this pointer over by 1 and slightly increase our guess. If the opposite is true, if our guess is too small, then we move this one over instead. And we keep going in a loop until either we find a solution where they are equal to each other, or we hit the case where the left pointer and the right pointer cross over. Because once they've crossed over, we're basically only going to be repeating things that we've already seen before, right? We've already probably been in the position where left and right were next to each other. If we switch them, we're just going to be repeating things we've already tried. So we'll say, we'll have our first pointer be int left is going to be 0. And then we're going to have int right is going to be equal to a dot length minus 1. So it starts at the other end. And then while left is still less than or equal to right, it can be equal to, we'll go through our 3 cases. So if a left plus a right equals x, then that's great, we're done, we return true. Else if a left plus a right is less than x, then we know that we have to increase the smaller of the 2 pointers, right? So all we have to do is left plus plus. You can also do left plus equals 1, up to you. And lastly, we handle our last case, which is else, which is also just if a left plus a right is greater than x, we do right minus minus. And of course, if we break out of this for loop and we never found our solution, then we know that there is none. So at the end, all we have to do is return false. This is a really tricky problem. It's not hard once someone shows you the solution, but it's definitely really hard to come up with a solution all by yourself. Okay, now, real quick before we move on, what is the runtime of both the original and the improved versions of our algorithm? But this is one of those cases where the upper bound and lower bound don't quite match up, so we can't really make a theta bound here. So in this case, the upper bound is, okay, the assumption that we never hit this case, and so that'll require us to go through both sets of for loops, which is going to take us O of n squared time as our tightest upper bound. The best case is that we immediately hit it, that we don't even have to do anything else, which in that case is omega of 1. Now, same thing over here. The best case is again going to be omega of 1, because what happens if we just immediately hit this case and we're like, great, we're done, we're over with this. The worst case again is that we have to go through everything. Now each time we're going to be either incrementing left towards right or right towards left. So in the end, since we only stop once they basically meet up, it'll take O of n time for that to happen, which is a lot faster than our previous answer, which is fantastic. So that's number 3. Now we're going to move on to our extra problems. So specifically CTCI. So the first problem asks you to write a union function that returns an array that is the union between two given arrays. So this question's a little hard, so I'll give you guys a bigger hint than the worksheet gives, which is try using a set of some sort because of the way, because of the fact that sets cannot have duplicate items, right? So try using a set and we'll reconvene in a minute. Okay, let's do this problem together. So the first thing I'll do is set up our set. So I'll say hash set. Doesn't super matter which set we use, but we haven't really gone too deep into sets yet, so I'll just use hash set. Integer set equals new hash set. Bam. So we have our set set up. Now, all we're going to do is add everything from A and everything from B to our set. So, for int num in A, all we're going to do is set dot add num, and then we're going to do the same exact thing for int num in B, set dot add num. And if there's any repeats, the set will not add them twice, it'll only add them once. So we have that set up, and now we have to figure out how big is our array going to be. And again, we can use our fancy ADT. So it doesn't really matter how the hash part works, we haven't covered that yet, but we do know that sets work. They have three main functions, right? They have dot add, which we've already used, which lets you add some item. They have dot contains, which lets you check whether some item exists in the set. They have dot size, which returns the size of the set. And the last thing that they have is an iterator, because all sets are iterable. So dot iterator, and this will return an iterator over all of the items in the set. So based off of that, now we've used this one, and now we can use size to figure out how big to make our union array. So int array union array equals new int set dot size. And now we have that. We can go and use our iterator for int num in our set. Doesn't really matter what order they come out in. Union array. Oh, we should probably have an int I equals 0 up here. Union array I equals num and I plus plus. And then all we have to do at the end is return our union array. Great, that's our union. Now we're going to get something a little trickier. So the same thing, except this time instead of returning the union of two sets, which is all the items they have in common, we're going to return union of two sets, which is all the items that they have without duplicates. We're going to return the intersection, which is all the items they specifically have in common. Again, please use the ADTs that we've talked about in the past, because otherwise this problem gets really, really, really hard. I'll give you guys a couple seconds to think about it. So here we're going to actually get a little bit tricky. So first of all, we're going to instantiate two hash sets. So we'll say hash set, integer, and this is going to be just set of A equals new hash set. This will only contain items within A. And then we'll have a second one that actually contains the intersection. Because if you recall, I said there were 4 functions and we only ended up using 3 of them. So in this version, we're going to use all 4. So we'll have hash set integer again, and this one will be the actual intersection. Great. So the first thing we'll do is just dump everything from A into the first hash set. So for int num in A, set of A dot add num. And now that we've done that, we can go through all of the items in B, and this time, before we just dump them into the intersect function, we're going to compare it to set of A and make sure the item is contained within set of A. So we can do for int num in B if set of A dot contains num then we're going to do intersect dot add num, but only if they're both in there. And now the rest of this is going to look very similar to our previous thing, where we will just create a new array with the size based off of what the set.size. So intersect array equals new int intersect dot size. And then now that we have that, we can have I equals 0, and then for int num in intersect array I equals num. And now we can just return it. Great. And that's it. We are done with our worksheet for today. I hope you guys found this helpful. Please leave feedback for my videos in the weekly forums. I would love to hear from you if there's anything I can do differently. This is my first time making these videos for this class, so I'm just kind of playing it by ear. But yeah, have a great week, and I hope to see all of you next week. Good luck!